the next topic is metapopulations. And this is a group of loosely connected populations connected by dispersal. So there are individuals moving back and forth between smaller subpopulations. So these are some examples of different populations or different ways that metapopulations might look like. So this is not a metapopulation. These are three independent populations and individuals do not move between them. So this is not considered a metapopulation. You need these arrows, and the arrows mean that there are individuals going back and forth between these populations. And the direction of arrows indicates the direction of movement. And assuming those individuals that move end up breeding in their new area, then that also means the exchange of genes or gene flow. So this population here is a simple one with three interacting populations, and there are individuals going back and forth between the different subpopulations. This is an example of a metapopulation with a large core population and three satellite populations. And you can see this population is producing lots of extra individuals, and the individuals are only going towards the smaller populations. The small populations are not producing enough extra individuals that they make it back to this larger core population. This one is more complex. You can see that there's a large population and then a medium-sized one and some smaller ones. And this large one contributes individuals this way, but some of these other ones also contribute individuals in other directions. So these large core populations are called source populations. They are large enough that they're producing extra individuals that support other smaller populations. They're large enough that these populations are growing. So if they're producing extra individuals, that means that population is growing. These small populations are called sink populations. They're declining. They have negative population growth. The only reason they keep existing is by the extra individuals produced by the source population. So the source population is supporting the sink populations. And so we see this is an example of a real population, a real metapopulation, of bighorn sheep. And so we can see that the red are permanent populations, the purple are reintroductions, the yellow ones are natural recolonizations. And so you can see, and I think the orange ones are just other potential habitat. And so you can see there's some major barriers here. So we have metapopulations where we have movement back and forth among these different areas. Some of these have resulted in colonizations to new natural recolonizations. And then there are these major barriers. So the black indicate roads. So this is I-40, which is fenced. And you can see there's a metapopulation here. And this is not that far, but those sheep can't cross the road because it's fenced. Similarly, you see connected populations here. But this road here, I-10, is a major barrier, and they're not crossing that. And so this is what it might look like in a real population. The number of populations in the metapopulation is really important for extinction risk. And metapopulations are thought to be something that buffers areas from overall extinction. And the idea is that metapopulations are dynamic and that small populations might go extinct, but then they might be recolonized if you have these metapopulation dynamics. The idea is that one might blink out one year, but then it's going to be recolonized by the other areas. And then a different one might blink out several years later, and then it gets recolonized because of these dynamics of movement between the different areas. And that allows gene flow and the protection of genetic information and the protection of the overall population, because the likelihood of all the different populations going extinct at the same time is usually very low. And so they can kind of support each other and recolonize areas when they blink out. So this looks at the probability of extinction with different numbers of populations, and then we have the number of time. And this is for a plant. This is a thistle. And so you can see if you add one population over time, the probability of extinction goes up because the longer it is, the more likely it is that something's going to go extinct. In a very short period of time, the probability of something go extinct is very low, which you can see here. And so if we want our population to last 50 years, then and we want the probability of extinction to be as low as possible, you can see we can get it down to about 47% or something like that. 47% probability of extinction if we add 100 populations. If we only add one, in 50 years, they're almost certainly going to go extinct. And so you can see as we add more and more populations, we decrease the probability of extinction through time if we're looking at the same number of years.